All right, so again, just want to talk a little bit about harmonic functions. Hit the key points of these things. I'll make some more videos about heat flow and the Dirichlet problems separately. This is just a basic video on harmonic functions. So we saw with analytic functions that the real and imaginary parts have to satisfy the Cauchy-Riemann equations. Something I do want to say here, which again does cause some confusion, is when you see this notation, it's called Leibniz notation for derivatives, this d over dx or df over dx. It means take the derivative of the function f with respect to x, say. Well, these are operations that act on a function. So there are four second derivatives, partial derivatives, when you have a function of two variables. And this is the notation. The point is, this is an operation. It acts on a function from the left. So whichever letter x or y is closer to f, which is on the right of these symbols, that's the derivative you're taking first. But when we use subscripts, we have everything's reversed, how we deal with subscripts. So I just want to clarify that for some of you. So when we write u subscript xy, what we're really saying is take the derivative in x first and then in y. So that corresponds to the Leibniz notation d squared u over dy dx. All right, so just again, that's just fact of notation. You have to understand, and it doesn't really matter for our class anyways, because the functions we deal with always have continuous derivatives of essentially all orders. Especially when we're talking about harmonic functions. Analytic functions have derivatives in z up to all orders, so their real and imaginary parts have partial derivatives in x and y of all orders. And those are continuous functions, and so the order in which you differentiate such functions doesn't matter. So we always have, for example, if u or v is a harmonic function in particular, the mixed partial derivatives, where you take one in x and one in y, the order of that doesn't matter. So what that means is the bottom line here on this first page is, because of that fact, the real and imaginary parts of an analytic function are going to be what we call harmonic, meaning they satisfy this equation that the second partial derivative with respect to x plus the second derivative in y always adds up to 0. And that's actually the definition of what it means to be a harmonic function. And we use shorthand, this triangle or delta, Greek letter delta, as the Laplacian operator. So when you see that in front of a function, it just means compute the derivative, the second derivative in x and the second derivative in y, take those two functions and add them together, and that's your function, delta g in this case. So harmonic functions were really defined in this real setting. The fact that they are connected to complex functions, analytic functions, is in a sense a bonus. These properties were all studied at the same time long ago, and that's part of the reason why complex numbers were thought up, basically, to allow for simplification of a lot of calculations for these more complicated real valued functions of more than one variable. So again, let's consider a simple example down here at the bottom, e to the 2x times sine of 2y. Again, taking two derivatives in x and then 2 in y, you see that you get 0 when you add those together, so this is a harmonic function. So let's find the harmonic conjugate of it. So again, we use the Cauchy-Riemann equations. So we take u sub x, we compute what that is, all right, and then we set v of x and y, the original function for v, equal to the antiderivative of that. But the antiderivative is taken in y, because u sub x has to equal v sub y. But when we take antiderivatives, we can do that, and then we always have to keep track of some unknown constant of integration, because these are not definite integrals, they're indefinite integrals. But since we're taking an antiderivative in y, that constant could be actually a whole function in x, because x isn't changing. When we differentiate in y, we're viewing x as not changing, so it's fixed. And then we do the same thing. We take uy. We determine what that is. In this case, it's very simple. Just a chain rule. There's no product rule here because the exponential and the sine terms are separating the variables x and y, so there's no product rule here. Just we have to apply the chain rule because of the 2 appearing next to the variables. So in this case, we have use of y, and we set v of xy equal to the negative antiderivative with respect to x, because that's what the Cauchy-Riemann equation says. The second Cauchy-Riemann equation says use of y equals negative v sub x. We do the same thing. We pick up the constant in y. Now, in this case, we set these quantities equal to each other, and we see that they're both the same thing, but each one is plus a function in x and one is plus a function in y. Well, the only way a function in x and a function in y can be the same is if they're both a constant function, and we can pick a constant anything we want. Let's pick 0. All right. If we picked them both to be 5, we'd still have a valid harmonic conjugates. So harmonic conjugates aren't unique, but up to a constant. You can add a constant and it's still a harmonic conjugate. Let's just pick 0 in this case to simplify things. So that means that this function u of xy plus I v of xy, which I've written here in the bottom, is an analytic function. I notice in this case, because of that separation of the variables, x and y, in different factors of function u of x and y, this generally happens when you have that. What you have is these functions c1 of x and c2 of y generally will become 0. They'll be 0. And the next example, I want to show you what happens when the variables aren't separated. When they're not separated, oftentimes you have to make some choice other than 0 for these functions. So we'll consider this u of x and y is x to the 5th minus 10x cubed y squared plus 5x y to the 4th. Again, making these up is quite easy because we know power functions are analytic, z to the 3rd, z to the 5th. All I did here was take z to the 5th, where z is x plus iy, and I expanded that out using the binomial theorem, and then I made u all the terms that don't have an I. So actually, we already know what from the binomial theorem, I could actually already know what the harmonic conjugate is, but let's practice with our practice this skill. So again, we confirm very easily that this is a harmonic function. Just take 2 derivatives in x and 2 in y, add them together, you see everything cancels. And now we move on to finding v. So the Cauchy-Riemann equation says ux, well, ux is equal to this 5x to the 4th minus 30x squared, y squared, plus 5y to the 4th. So we anti-differentiate that with respect to y, and we get one value for v of xy. And this one has the c1 of x, which is some unknown function of x. And we'd use the other Cauchy-Riemann equation. So we figure out what u sub y is, just differentiate really simply in y. It's just polynomials in y and x, so it's pretty easy just using the power rule. And then we set v equal to the negative antiderivative of that with respect to x, because that's what the second Cauchy-Riemann equation says. It says that v sub x is negative u sub y. And then we get these two quantities, we set them equal to each other, we see that they have some things in common. They both have a 5x to the 4th y. They both have a negative 10x squared y cubed, and there's a y cubed missing in I miscopied something here. Alright. Let me go ahead and see if I can quickly fix that. Right, so we're here in the middle again. In this case, we have, and we set these things equal to each other. So again, they share two terms in common, but the first thing we did, which picked up this c1 of x, there's also a y to the fifth. But in the other one, there is no third term, but there is this function of y, c2 of y. So since there's no function of x on the right, so we set c1 of x equal to 0, and then we set c2 of y equal to the y to the fifth because that's left over. And then that tells us what v is. And again, we have a harmonic, an analytic function. If we put these functions u and v together, u plus iv creates an analytic function. So again, in this case, we couldn't just set these c1 of x and c2 of y equal to 0. We actually had to kind of look at the equation to pick what those are. And the reason for that is because x and y appeared in the definition of our function u mixed together. There were terms where x and y were actually multiplied together.